if I have, let's say, a buffer that's made of a weak acid and a conjugate base. For example, HC2H3O2 with C2H3O2 negative. Now, this buffer will resist the pH change if you add a strong acid or if you add a strong base. It will resist both. Okay? For example, if you add a strong acid, such as HCl, then the conjugate base part of the buffer will react with the HCl. Okay? And if you were to add a strong base, like NaOH, then the acid part of the buffer will react with the NaOH. See what's happening here? So the acid with the base, and the conjugate base with the acid. So, for example, let's just say we added HCl, and I'm going to ask you for the net ionic equation. Okay, so if you wanted that an equation, and we're dealing with a strong acid as one of the reactants, what part of the strong acid do we include?
Nothing. Nothing?
No, if it's strong acid, we just keep the H plus. Okay. Now, HCl will be reacting with the conjugate base, which is, is going to be fully kept.
Add HCl to like what?
Add HCl to the buffer.
Okay.
And they say write the net ion equation. So we're going to, from the HCl, take the H plus part. From the buffer, take the conjugate base. Make it a double arrow or a single arrow, it doesn't matter. And you will get HC2H3O2. So that way we were able to, change the pH only slightly. Now adding HCl is going to make the pH drop, but because it's a buffer, it's going to only drop slightly. So the pH decreases slightly. Now if we add NaOH to buffer, from the NaOH part we keep the OH negative, right?
Yeah.
From the buffer we keep the acid part, which is HC2 and H3O2. And we're going to get two things, because now the OH with the H will react.
H2 and C2H3O2?
C2H3O2 negative, yes. And that's how the buffer works, essentially. So in this case, the pH will increase, but only slightly. Now, one of the things about a buffer is that the higher the concentration of its components, the better. So for example, imagine if your buffer is made of HC2, H3O2, and C2H3O2 negative. If they are both 0.10 molar, that's okay, but if they're both 0.50 molar, that's actually going to be better. So the higher the concentration, the better they can resist pH change more. Okay? So that's one thing to make a buffer better.
So this is a conjugate base and this is the weak acid, right?
Exactly, that's the conjugate base and that's the weak acid. So to make a buffer better, you want to make the concentrations more, or you can make the concentrations close to each other. For example, if they are both 0.10, that's better than one of them being 0.10, one of them being 0.5. It's better to keep them close to each other. Okay. Now, a buffer will be having its pH calculated in a special way by a special equation that's found in your equation sheet. pH is equal to pKa plus the log of the conjugate base, which we term as A negative, and the weak acid. So A negative is the conjugate base, NHA is going to be the weak acid.
And this is to find.
This is to find the pH of a buffer system. If there is buffer, because why? Because if there is buffer, you will have both weak acid and a conjugate base at the same time. So you have to use this equation to account for it. And of course, pKa is equal to the negative log of Ka. You know what that is, Ka? It's called the acid dissociation constant. Ka is for a weak acid. Each weak acid has its own Ka. Okay. Ready for some problems? So I'll just say that we have HC2, H3O2, and C2H3O2 negative buffer, and the concentration of the acid is 0.20 molar, and the concentration of the conjugate base is 0.50 molar, and the Ka is 1.8 times 10 to the power of negative 5. We're going to now say find the pH. So how would you find the pH? First of all, is it a buffer system?
Yeah.
Because we have both acid and conjugate base. Not because it's a buffer. Like, they won't even say that a lot of times. You just have to know if they both exist, it's a buffer.
You can have a conjugate acid and a base, right?
Yeah. Of course you could do that too. But that's very rare. So we're going to say pH is equal to pKa plus log conjugate base over weak acid. Now pKa just means, in your calculator, negative log of 1.8 times 10 to the power of negative 5. Plus log, we have the conjugate base, which is
the concentration.
The square brackets mean concentration. The conjugate base is the negatively charged one, which is the 0.50 over the 0.20. And, you can do it in the calculator and let me know how much you get.
This right though.
So you got 5.14,
42.
you mean? Okay.
Same thing. Can you check if it's the correct answer?
It is. Yes. But the book has made a mistake. It only put 2 sig figs. You must always put the pH as one more sig fig. Okay. Now, the best buffer is when the concentration of the weak acid is same as the concentration of the conjugate base, because the log of the conjugate base over the weak acid is like saying the log of 1, and log of 1 is 0. Okay?
You said this is a conjugate base?
The A negative is the conjugate base.
Hydrated conjugate acid.
If you are dealing with conjugate acids, you must have a base to begin with, like ammonia. But most of the exam is going to be dealing with a weak acid. Most of it, at least. So the log of 1 is going to be a 0. And so when the log of 1 is equal to 0, pH is equal to pKa plus log of 1. So pH is equal to pKa. Okay?
When do you use this?
Whenever the concentration of the species involved in the buffer are the same. pH is going to be equal to pKa. Now, why is that important? Because as you can see here, we're going to be dealing with a titration curve graph. And we're going to be having pH on the y-axis and the volume of something added on the x-axis. And most of it's going to be volume of the base added. Because in most of the situation, the pH will rise. And for the pH to rise, you have to be adding a base. Now, it might start like this, slightly rising, then jumping, and then slightly rising again. That's what it looks like for most of the situations. Now, the midpoint of the semi-horizontal line is where the pH is equal to the pKa. That's the midpoint. And for that to occur, that's when the conjugate acid and the conjugate base and the weak acid have to be the same concentration. Okay? So pH is equal to pKa, midpoint of the first horizontal line. pH is bigger than pKa here, and on the left pH is less than pKa. Okay. Now, in the midpoint here of the semi-vertical line, we're going to say the mole of the acid is equal to the mole of the base. Okay? They're going to have the same mole as each other. Good? Okay. Let's do some math. So, let's take, actually before the math part, if we're dealing with a weak acid and a conjugate base, the best buffering point is when the pH is equal to the pKa. Okay?
Which is the same thing as having the same concentration, right?
Yeah, so when the concentrations of them are the same, pH is equal to pKa. Now, when do we say that pOH is equal to pKb? If you're dealing with a weak base. So if weak base concentration is equal to a conjugate acid concentration, we say the pOH is equal to the pKb. Okay? So you have either pH is equal to pKa if you deal with a weak acid, or pOH is equal to pKb if you're dealing with a weak base. Kb for base, Ka for acid. Okay. Let's do some more reactions. Imagine if I have a buffer system made of ammonia and NH4 plus. Ammonia is the weak base, NH4 plus is the conjugate acid. And now imagine if I add HCl to the buffer. Can you write me the net ion equation?
The ionic equation.
Net ionic.
Okay.
So from the HCl, what do you keep?
You write OH for the NH.
One second. So you're gonna add HCl to the weak base or to the conjugate acid? That's the first thing you should know.
The HCl to the weak base or conjugate acid?
To the weak base, right? Because acid reacts with base. For the HCl part, only keep the H plus. And if it's a weak base, keep the whole thing, as we've spoken about earlier. And you get NH4 positive. Is that easy? Nothing confusing, right? Acid reacts with base. Now, what if I add NaOH to the buffer? What's my equation going to look like now? From the NaOH, I only keep the OH negative part, correct?
Yep.
And I'm going to have to add it to the conjugate acid, which is NH4 positive. You will get water plus NH3. Okay?
You can go up. So when you add HCl, so which ones like do you use? This is the product, and this is
No. So look, in a buffer, you always have two things. So if you're adding a strong acid, you make it react with the weak base of the buffer. But if you're adding a strong base, you make it react with the
acid.
conjugate acid part. Okay? Okay. So look, before you use the calculator, you have to understand and plan the situation. You're reacting HCl with a buffer. How would someone like me know it's a buffer? Because we have both the acid and the conjugate base present at the same time. Now, the strong acid HCl would react with which one of the two species?
The base.
The conjugate base, which is which one? The acetate, correct? Because HCl with acid just won't work. So it's like having HCl plus the conjugate base. Let's make that ion equation for that one. So HCl becomes H positive. And acetate, you have to know before the exam, is C2H3O2 negative. You will see acetate a lot in the exam. Becoming HC2H3O2. So far, so good? What are the concentrations that we have provided? You see, in the case of adding a strong acid or a strong base to a buffer, you have initial concentration for everything. Nothing starts with 0. Nothing. For example, the H plus is 0.10. The conjugate base, 0.50. The acid, 0.20. In these scenarios, you have to work with the ICC table. Okay? Now, you've been told before that the ICC only works with moles. But in the case of buffer systems, it's allowed to work with molarities. It's allowed to. Now, how many reactants do you have?
2.
Which one becomes 0? Which one gets finished first? The lesser one. So 0. So you're going to do minus x, plus x. So how much is the x?
0.10.
Exactly, x is 0.10. So 0.50 minus 0.10 is 0.40. And 0.20 plus 0.10 is 0.30. So now we're going to say pH is equal to pKa plus log of the conjugate base over the weak acid.
Go up. Why can you use these concentrations for this equation?
Because these concentrations are before the acid was added. But now the acid being added will change these concentrations.
So this is after the acid.
That's after the acid is added, exactly. Now we're given Ka. It's called acid dissociation constant. It's given to us as this number. So we're going to say negative log of Ka plus log of conjugate base over the weak acid. And you will get the answer. Okay? Yeah. You will write OH negative with,
Acetic acid.
which is what formula? You have to know by now. HC2H3O2. To give you what?
To give you C2H3O2 negative.
Mm-hmm.
And then you do ICC table.
And H2O.
Because the H reacts with the...
Exactly. Now, what are the concentrations that I put under each one?
So for the OH will be 0.10. The acid 0.20, and this will be 0.50.
ICC. Of the,
Minus X.
minus, so basically 0 here. Minus x, plus x. And so x has to be
0.10.
0.60. Okay? So now the rest is easy, right? Just do the same equation and put the numbers.
What is the equation called in general?
Henderson-Hasselbalch. Okay. Now, if you have HCl inside a container and you have NaOH inside a different container, and if you know the concentration of the NaOH but the concentration of the HCl is unknown, you can find out the concentration of the HCl by carrying out a procedure called titration. So titration involves you adding the NaOH to the HCl until at some point there is going to be a color change. That color change has to be very precisely happening at a certain pH. If it happens at the wrong pH, you cannot find the correct molarity. So that means to have the color change occur at the correct pH, you have to pick the correct indicator. So what exactly is an indicator? It's a weak acid that will have two colors, one before dissociation and one after dissociation. So before dissociation it has one color, after dissociation it has a different color. So far so good? We refer to it as HIN. H because it's an acid and IN means indicator. Now everything here is going to be aqueous. And the rules of Ka says If everything is aqueous, you have to include everything. You put the products over the reactants. So the color change of the indicator happens at a specific point called the endpoint. At this point is the point when the concentration of the weak acid and the concentration of the conjugate base is the same as each other.
The endpoint?
The endpoint is when the concentration of the conjugate base of the indicator and the concentration of the indicator itself is the same as each other. So that means that they're going to be the same as each other. So when you look at the Ka expression, the ion negative and the H ion will cancel each other, leading you to Ka is equal to H positive concentration. Now, if you were to take the negative log of both of these quantities, the negative log of Ka, you would say, is equal to negative log of H. And negative log of K is equal to pKa. Negative log of H is equal to pH. Okay? So that means that the color change occurs when the pK and the pH are the same as each other.
The color change?
The color change will happen when the pK and the pH are the same as each other of the indicator.
Are we going to do an equation on this now?
No, just words. So how do you know what to pick when it comes to the indicator? Because it has to change its color at a very certain pH. For example, if you're dealing with a strong acid and a strong base, the pH at the equivalence point, we call it. So look, what's an equivalence point? You draw this curve here. That's the equivalence point. The midpoint of the semi-vertical line. This is called the equivalence point. It's going to be it's happening at the pH of 7 if you're mixing a strong acid with a strong base. So in that case, the pKa of the indicator has to be very close to 7. So it can change at the moment when you have the equivalence point. So what you're essentially seeking is to keep the endpoint and the equivalence point as close to each other as possible. Okay? So if the equivalence point is 7, endpoint has to be either a bit less or a bit after. If you're dealing with a strong acid and a weak base, which one is going to win? The strong acid. That means the pH of the equivalence point will be less than 7, maybe 6, maybe 5, for example, right? If you're dealing with a strong acid and a strong base and a weak acid, the strong base is going to win. With the pH at the equivalence point, that's more than 7. But if you're dealing with a weak acid and a weak base, we don't know which one is going to win without looking at the information of the Ka and the Kb. So the Ka, suppose it was bigger than the Kb, then the pH will be less than 7 because the acid is going to win. And if the Ka is less than the Kb, the base will win, the pH will be more than 7. Okay? So always make sure to choose the indicator whose pKa is very close to the pH of the equivalence point. Very close. Now, when you carry out a titration procedure, you have to use a burette. You also have to use a flask. So, if you recall back the example of the HCl and the NaOH, and I knew that the NaOH was 0.30 molarity, but the HCl was unknown molarity. In this situation, the one with the known concentration will go inside the burette. And the one whose concentration we're trying to find will go inside the indicator. Okay? So, inside the flask, and the indicator will also go in the flask. So the substance, you don't know its concentration, goes in the flask. What also goes in the flask? The indicator. Okay?
The indicator is a color?
It will color change at a certain point, yeah. Yeah. The burette's going to be kind of weird when it comes to the reading. So it looks like this, and it's going to start from 0 on the top and will go all the way to, say, 50 in the bottom. So it's like reading it upside down in a way, you know? Because like right now, if I give you a graduate cylinder, it will go from 0 to maybe, let's say, 50. But a burette is going to be the exact opposite. It's like an inverted tube, essentially. Okay. Now, if you're dealing with a monoprotic acid, which means an acid that can only give away one H plus, then at the equivalence point, the mole of the acid is equal to the mole of the base. Now, if you recall, molarity is equal to mole over volume. So mole is equal to molarity times volume. Cross multiply.
Yeah.
So essentially, molarity of the acid times the volume of the acid is equal molarity of the base times the volume of the base.
And if it's a polyprotic acid, it won't be equal at the equivalence point?
They will be, but you have to implement a different equation. I'll show you. So at the equivalence point, all the acid that was in the flask got neutralized by the base. Okay? All the acid that was in the flask. Okay, so the acid had unknown concentration. That's why it was in the flask originally. But if you're dealing with a polyprotic acid, so something like H2SO4 or H3PO4 or H2CO3, you're dealing with this equation essentially. MA times VA is equal to MBVB over coefficient of the base from the equation.
What would the coefficient of the base be?
Most likely a 2. Because look, if I take a polyprotic acid like H2SO4 plus NaOH, what will I get? Na2SO4 with water. And if I were to now balance it, I'll put a 2 in here and also a 2 in here. So it's going to be most likely a 2. Okay. So let me draw you the titration curve. So it starts low and goes up high. That's if you are essentially adding a base to an acid. And here, the midpoint of the semi-horizontal line is called the half equivalence point. This is the midpoint of the semi-horizontal line. Okay? What happens at the midpoint? The pH is equal to pKa. That's because the concentration of the acid is equal to the concentration of the conjugate base. Yeah?
Not the base?
No, conjugate base. Like for example, the concentration of the HC2H3O2 is same as the concentration of the C2H3O2 negative.
So this is supposed to is this supposed to be a titration about a buffer?
Titration will almost always include a buffer inside of it. If you see the horizontal line, that's where the buffer is acting. The best point of it is in the midpoint. And here, the vertical line midpoint is where the mole of the acid is equal to the mole of the base. Okay, let's explain to you more. So, that's the midpoint. On the left of it, the acid concentration is more. On the right of it, the conjugate base concentration is more. And toward the end, where the pH is very high, you have a lot of OH negative, because the pH may be jumping as much as the pH of 12, which indicates you have lots of hydroxide. Any questions?
No.
Okay. Now, if you're dealing with a weak acid plus a strong base, the strong base is going to win, which basically means that the pH at the equivalence point will be more than 7. How would you justify that in the AP? You would say because the conjugate base is now present in significant amounts, much more than the concentration of the weak acid. Much more than. So when the conjugate base is at a much higher concentration than the weak acid, that's where the equivalence point is going to be. Okay, going back here, if the equivalence point, say, required 30 ml of base, the half equivalence point is going to require exactly half. That's why it's called half equivalence point. Get it? So at the end of the titration curve, which is here, we have a lot of hydroxide ion. And that's because that's the equation happening toward the end. The conjugate base reacting with the water to give you acid along with hydroxide. This hydroxide gives you the pH of 12 or more.
At this point? Or
Yeah,
anything?
the last horizontal line, the last one. Let's now speak about the titration involving the addition of a strong acid to a weak base like NH3. Of course, you will start high and you will then drop, correct? Because HCl will be dropping it. The pH at the equivalence point, do you think it's going to be more than 7 or less than 7 or equal to 7?
Yes.
Yes, because the strong acid wins. And the half equivalence point is going to be right here. Right here. Okay? That's the exact point where the pOH is equal to the pKb. But here, the pH is equal to the pKa. So please be able to distinguish between the two.
The pH here is still 12, right?
I don't know. Probably less. I'm not sure. Doesn't matter. Doesn't matter. So what's pKa? It's negative log of Ka. And what's pKb?
Negative log of Kb.
Exactly. And don't forget that pH plus pOH is equal to 14 at 25 Celsius. Now the pH here toward the end is very acidic. And the reason is because you have lots of H plus concentration. So what's the equation occurring toward the end? It's because you have a lot of conjugate acid forming here. Lots of conjugate acid, that's why it's acidic. Reacting with the water to give you ammonia with H3O+, which is called hydronium ion. So if I say H3O+, or if I say H+, they mean the same exact thing. And you have lots of them toward the end. That's why it's going to be very acidic, maybe the pH of 2 toward the end.
How did you figure out this equation from this?
Because the most common species at the equivalence point is the ammonium. And if you react the ammonium, which is a conjugate acid by the way, if you react the ammonium with water, you get these two results.
Yeah, okay.